Namaste and welcome to the Data Structures and Algorithms class. I hope all of you read the question. Given two numbers, we need to calculate the greatest common divisor or the highest common factor. GCD and HCF are actually one and the same. And my dear friends, ability to calculate the GCD and LCM is a very important tool that you must possess, especially for those of you who want to crack your product-based companies and want to start your competitive programming journey. Definitely GCD LCM is a very highly reused concept. But it's not a very difficult thing to wrap your head around. Let me just quickly show you what is meant by a GCD and LCM. I have two numbers A and B. A is 20, B is 15, right? These are all the numbers between 1 to 20. These are all the numbers between 1 to 15. Now, what do you mean by a divisor or a factor? First, let's understand what do you mean by a divisor or a factor. Guys, it's very simple. Any digit which can perfectly divide a given number is naturally its divisor or factor. Perfect divisibility means what? When you divide, your remainder must be 0. That is what it means. And all of you know, 1 can perfectly divide 20, 2 can perfectly divide 20, 4 can divide 20, 5 can divide 20, 10 can divide 20, and definitely 20 can divide 20. Which means 1, 4, 5, 10 and 20 are the divisors or factors of 20. Similarly, if you take 15, 1 can perfectly divide, 3 can perfectly divide, 5 can perfectly divide, and then it is 15. Which means 1, 3, 5 and 15 are the divisors or factors of 15, and I am keeping everything this side. Now, look at the divisors or factors of 20 and look at the divisor and factors of 15 and tell me which are common. Naturally, you can notice only 1 and 5 are common, hence I will remove the rest and I will just keep 1 and 5 there. Now, out of 1 and 5, tell me which is the highest common factor, or tell me which is the greatest common divisor. It is nothing but 5, and hence I am just keeping 5 and removing the rest. 5 is both the GCD and the HCF of 20 and 15. I hope you are able to think. It's as simple as that. Now, what I want you to understand next is very simple. How are we going to use this concept? How are we going to use this concept, and how are we going to first of all solve or write an algorithm to find the GCD of two numbers? It's very easy. Look at this, guys. One thing that is very clear to me is I have A. Now, if you look at it, A is 20, B is 15. Tell me which is the larger number? 20. Which is the smaller number? 15. Now, if you use some common sense, tell me, these numbers, right, after 15, that is 16, 17, 18, 19, 20, these numbers, will they ever be able to be part of the GCD or HCF of 20 and 15? No. Because any number that is greater than 15 can never be common, because here it's only till 15, here these are numbers after 15. So these values are useless for me to calculate my GCD and HCF, which means common sense would tell me one thing I can do is first, given two numbers, find which is the minimum number. Minimum number is 15. Lay out all the numbers from 1 to 15. Now, if you look at it, I don't want to find the smallest common divisor, right? Or I don't want to find the smallest common factor. I want to find the highest common factor. To tell me the highest common factor, if you want to find, does it make logical sense to begin from the starting where all the smaller numbers are present, or will it make sense to begin from the ending where all the larger numbers are present? Naturally, it is from the ending, right, in the reverse order. So what I will do is find whichever is the minimum element. I will then start my iterations from the minimum element, and I will keep checking if this element, this ith element, is it perfectly dividing both A and B. If it is perfectly dividing both A and B, which is I mod A 0, I mod B 0, then I know that is a common divisor. And because I am starting from the ending, I also know that it is the highest common divisor. So the moment I find a common divisor, I will just break out of the loop. Otherwise, I'll keep coming behind, and I will keep checking. Which means if I have to just list it out as an algorithm, what will you do? Step number 1, find the minimum of A and B. Step number 2, iterate, that is use a for loop, start from I equal to minimum and go till 1. Inside the loop, check if in case I is a common divisor. Don't you think I can write that way? I is a common divisor. If I is a common divisor, return I. That's it. Simple algorithm. Now, naturally, we are not using any optimizations here. This is the first approach which came to our mind, right? The first approach that comes to your mind may give you the solution, but may not give you the solution in the most efficient way, in the most optimized way. And the first solution that comes to your mind without any optimizations in it is what we technically call as the brute force approach. And whenever we iterate over all the elements one by one to find whatever we are trying to find, we normally call it as brute force. There is no optimizations here. Any confusion? So this is a brute force approach to calculate the GCD or HCF of two numbers, right? Now, how are we going to do this? It's very simple code. Let me just go directly write some code for you. I think everybody has understood the logic. Let's code. Now, here what I'm going to do is, I will first have to take input from the user. So I'll tell scanner. Now that scanner is ready, I'll just import it as well. Next, what I'm going to do is, I will just go and I'm going to now start taking input from the user. So I'll tell int a equal to scan.nextInt. I just have to take two integers, right? Scan.nextInt. Next, I will tell, I'll just duplicate that line and make it as b. So now I have a and I have b as well. Cool. Now what you have to do is, you have to first find the minimum of a and b. As you can, let us assume a is 20, b is 15. You have to find the minimum of both. How will you find the minimum of both? Like this. If in case a is greater than b, then, or you can say a is lesser than b. If a is lesser than b, a is the minimum. So what I will do is, I want to store that minimum somewhere. So on top of this, I'll just create one variable. I'll call it as int min. Initially, let it be 0, right? And if a is less than b, a is my minimum value. So I'll store it in, no, you're wrong. I will store a's value in minimum. Any confusion till this point of time? Great. Else, what I will do is, I will store b's value in minimum. Any confusion till this point of time? Yes, sir, we understood. Now, all you have to basically do is, you have to now do iterations. Now, look at this. I'm just showing you. Now, if a is 20, b is 15, you know 15 is the minimum value. So, the 15 is the minimum value. I'm just writing numbers from 1 to 15. Now, what I want to do is, I want to write a loop where I starts from minimum and goes all the way till 1, right? How are we going to write that loop? Simple. For, I'll tell int I, start from min and go all the way till the last value. So, see, I greater than equal to 1 because I want to go from minimum backwards till 1. And obviously, one by one, it should reduce in value, I minus minus. Good. Any confusion till here, guys? Now, inside this, what am I going to do? Inside this, I have to check if whichever value I is referring to, is it a common divisor or not? How will you do that? If in case, if I is common divisor, it should perfectly divide both a and b. So, I'll tell a mod I, that's how I'll get remainder, right? A mod I, I'll check if it is equal to 0. That means perfectly divisible. And both conditions should be satisfied. And b mod I is equal to 0. Cool. I have put this inside. Any confusion? Now what are you going to do, sir? If this is true, then 100% you know that this is I is your GCD or HCF. So what I will do is, I will just print it. I will tell system.out.println and I will tell I. Now tell me, the moment you found a common divisor, greatest common divisor or highest common factor can only be 1, which means I don't want this loop to continue. Because you know, here in this case, obviously if I keep applying this condition, it will be false for 15, 14, 13, all that, and highest common, the first one that I will find is 5. The first one that I will find is 5, for which it will be true. Now what I want you to understand is 1 is also a common divisor or a factor, but it should not go till 1. The moment you found 5, it should now come out of the loop. So how do you forcefully break a loop? Break statement is there. So just come and I'll tell break. Okay. Now this is how you can write if everything you are dumping it inside the main function. But you can also write it as a function. How to write it we will see. But for the time being, let me just remove this and let me just put let me show you the output, right? So watch it. If in case I execute, it's waiting. A value 20, B value 15. 5 is the greatest common factor. Any confusion till here? Let's put some other re-execute it. Let's put something else. Maybe I'll put 30 and 3. Yes. So highest common factor is 3. Absolutely correct. I'll put 17 and 13. Tell me, is there anything other than 1 which is common between them, common divisor which can divide both? No. So I'll get 1. So it works. Our logic works perfectly, right? Now, if in case you want to write this as a function, I'll just go on top of the main method, and there I'll just tell static, because I don't want to create any objects. Static, what it has to return is a GCD, which is an integer, and I will tell GCD is the name of the function. And next, inside that I'll just go and I will tell it accepts 2 numbers, integer A, integer B. And what I will do is, inside the body, I'll just go copy this entire from if onwards, from int min you copy everything. I'll cut this and I'll go paste it inside GCD. And one thing here I have to do is, I don't want to print it because it has to return. So I'll just go here and I will change this to return I, because it should return it. Now you must understand one thing. The moment a return statement is encountered, control will anyways come out. It will come out of the function itself. If it comes out of the function itself, naturally it will come out of the loop. So the loop will anyways break. So there is no need for you to explicitly break, because the moment you tell return I, it will return it. So looping will stop. So I'll remove break. Cool guys. Now I'll come down and here down and I'll call the function. So I'll just tell system.out.println and I'll call GCD and I will pass my A and B value to it. Let's execute and check if in case this works, because whatever it returns, I'm just printing it. So let's execute. Yeah. So put the values. Okay, exception. What is the exception? It is telling unresolved compilation, or there's a compilation error. Where is it? This method must return int. Okay, go on top. So go on top. Yeah. Oh, what is the problem? It's not telling return. Okay. It's inside the loop. Okay. So the thing is, if this condition does not satisfy, if let us assume there is no common divisor, right? Usually there will always be a common divisor which will be 1, but anyways, what I'm trying to say is that basically Eclipse is telling me that, hey, listen, what if this condition doesn't satisfy, and what if this return never happens? If this condition satisfies, only return happens. So Eclipse is like, hey, if this condition does not satisfy and return does not happen, then this is such a function which will not return anything. So please can you put some return statement here? I will tell. So what I will do is I will tell return. Now think about it logically, okay? If control comes to this return, it means that, you know, ultimately there is no other common divisor other than 1. That is what it ultimately means, right? So what I will do is I'll just tell 1 like this, because, you know, if it comes here, it means that there is no other common divisor other than 1. So I will just tell 1. So these are expectations of the language which you must keep in mind, right? Execute it. If I execute it, then you can now see some 20, 15 I'll give. It will work correctly as fine. Okay. I hope you understood why we put this return here, because that is the expectation of the language. It's scared. What if this return never executes? Great. So this is the brute force approach to calculating GCD. Now what I want to do is, I would like to help you calculate the time complexity of this. Now how do we calculate the time complexity? Let me show you. Now let's analyze the time complexity, right? Very simple. Listen to me carefully. First of all, what are you doing here? You're calculating whichever is the minimum element, right? Now, don't you think calculation of this minimum element, either this statement will execute or this statement will execute, it depends upon the condition. So it's constant, only one of the operations will happen. So I can count the frequency of execution as 1, either this will execute or this will execute, so 1. So what I would further like to basically do is, let us just do it this way, alright. Let us take all this code, let us take all this, and I'm just going to reduce it, and I will just call it as I'm calculating the minimum of A comma B, like this. Would you agree, friends? I can write it that way, right? So if I can write it that way, then one more thing which I can basically be doing is, let me just take this on top, right? Okay. Now listen to me carefully. Here what I'm going to do is very simple. I'm writing the time and the frequency. So this operation is going to execute exactly once, constant. Whereas this operation, look at it, it's starting from min and going till 1. So in the worst case, it will start from the minimum number between A and B, whichever is minimum, and go till 1. So how many times will it execute? Min number of times. Plus that one time that this condition will become false. Till greater than or equal to 1, true. When it becomes lesser than 1, it becomes false. Which means, one way to write it is, this statement will execute for min plus 1 times. How you should tell n? I am telling min, because here it is not n which is deciding the number of times. It is min. I hope you are able to think. If whatever is outside will execute min plus 1 times, then whatever is inside will execute 1 time lesser, which means this if statement will execute for min times. I hope you are able to think. And then if you look at this return statement, don't tell sir that will also execute for min times. No, no, no. This return statement will execute for only once, because the moment you hit return, control goes outside. So no more looping will happen. So how many times will this execute? Just once, which means I can tell 1. Would you agree with me? So if you add all the frequencies up, you can see you will get something like 2 min plus 3. That's what you will get. 1, 2, 3 and 2 minimums are there. Obviously, you know the 2 rules to simplify time complexity. You have to remove the constants. If I remove the constants, I will have min. I hope you are able to think. Which means one way for me to write this time complexity will be big O of, I will tell min, but just telling min will not make sense. So I will tell min of A comma B. Whichever is the minimum of A comma B, that many times it will execute in the worst case, big O. Are you able to think? One way of looking at this is, if min was n, it is big O of n, which means, how does this time complexity look? How does this time complexity look? It is linear. I hope everybody is able to think. Naturally, this is linear time complexity, right? So this is only your big O of min of A comma B. This is how it looks, linear, just like big O of n. Are you able to think? Clearly, as the n value grows, 100% time will also grow. Proportionally it will grow. So this is not good for us. It's not good for anyone. So is there more efficient ways to do it? 100%. We will look at it. Anyways, I hope this GCD program in the brute force approach and its complexity is clear to everyone. Now the previous brute force approach that we wrote, right, is definitely not efficient. For example, if the two numbers were 173 and 133, naturally the smaller number is 133, and hence you will have to iterate from 133 all the way till 1. And you know there is no common divisor between 133 and 173, which means you will go till 1, right? And hence 133 times you would have executed it. If in case it was 1733 and 1333, if these were the numbers, minimum number is 1333, then obviously there is no common divisor between both of them except 1, which means 1333 times your loop would have executed. So you can see, the larger the number becomes, the time that your algorithm is going to take is going to proportionally increase. And that is what we as people who are aiming to get into product-based companies must try to avoid. Our algorithms must be as efficient as possible, right? So I hope you're able to see why big O of n is a problem. As the n size increases, the time is going to proportionally increase, We have to avoid this. Now, we have a savior, and unfortunately he is not with us today because he was present, thousands of years back. His name is Euclid of Alexandria, a very, very famous mathematician, right? He has come up with n number of theories and hypotheses, and which is even today used in modern day mathematics. Now, Euclid realized that he needs to find a very efficient way to find the GCD or the HCF of two numbers. Now, Euclid, after immense observation and study, saw a pattern emerge. Now, what is that pattern? Let me show you. Let me take you to Eclipse. Now, watch it carefully, all of you. Look at what an amazing observation Euclid made, okay? Now, our two numbers, A is 20, B is 15. Now, look at this, guys. If I calculate the GST, we have already written the code, I'm just executing it. If you calculate the GST of 20 and 15, watch it. And I press enter, clearly it is 5, isn't it? Now look at the beauty. What Euclid said is, listen, find the larger number between both of them, that is 20. Find the difference between the larger number and the smaller number. So 20 minus 15 is 5. And he said, replace the larger number by the difference. So the larger number is in A, which is 20. I will replace that by the difference, which is 5. Now my two numbers change. It's not 20 and 15, it is 5 and 15. But you want to see something interesting? Re-execute. Now I'll find the GCD between 5 and 15. If I press enter, same. Interesting, isn't it? Look at it. Euclid said continue. Now again the larger number is 15, smaller number is 5. Difference between them is 10. Replace the larger number by this difference. Larger number is 15. Replace that by 10. So now my numbers are 5 and 10. Would you agree with me? Let us calculate the GCD. 5 and 10. If I press enter, 5. Numbers are changing. The GCD is the same. So interesting, isn't it? Similarly, he said continue. Again, larger number is 10, smaller number is 5. Find the difference, it is 5. Replace the larger number, which is 10, by the difference, which is 5. Both became equal. A and B became equal. The moment it becomes equal, he said stop. Stop and return any of the values, any of the numbers, because both the numbers will now have the greatest common divisor or the highest common factor. And you can see the number of operations you're doing is significantly reduced. Don't you think this is a more efficient way of calculating the GCD? And we have Euclid, the great mathematician, to thank for that. Anyways, if I have to I'll just remove this. If I have to just show you as an algorithm. So the algorithm is, first one, find the larger number. This is Euclid's algorithm. Second one, replace the larger number by the difference between the larger and the smaller number. Step number 3, repeat the first step and second step till both numbers are equal or become equal. Step number 4, return any one number, which is your GCD. I hope you're able to think. So I hope the algorithm is clear to you guys. I'll just keep the algorithm this side and let us quickly go and write the code. Watch it. Now, I'll just go here and I'll just create another static function. I'll call the static function as Euclid GCD. Euclid GCD. And it has int A and int B takes. Good. I'll come inside that. And as you can see, I have my algorithm here for reference. First thing you have to do is find the larger number, subtract the larger number from the smaller number, replace the larger number by this difference. How can you do all of that? Like this. I'll just come and I'll tell if in case A is greater than B. A is greater than B. Then clearly you can notice one thing, that if A is greater than B, A is the larger number. Now find the difference between A and B, A minus B, larger minus smaller number. Step number 2. How are you able to think? Step number 1 is find the larger number. Step number 2 is find the difference between the larger number and replace the larger number by this difference. This is the difference. Larger number is A, so replace the value of A by this difference. So I'll assign that to A. Simple. That's all. Else means B is larger than A, which means B minus A you do. And since B is the larger number, replace B value with this difference. That's all Euclid is saying. Hope you're able to think. Now, this is your step 1 and step 2. Step number 3 says, repeat step 1 and 2 as long as A and B become equal. They have to become equal. Or one more way to do this is, say this is, repeat as long as A is not equal to B. Because the moment A and B become equal, you must stop. So how will you do this? I'll cut this and I will put it within a while loop, because condition based looping I want. And I will tell as long as A not equal to B. What to do? Come inside and just paste whatever I've copied. That's it. Simple. Now, when you come out of this loop, what would have happened is, you would have found the GCD. So either you return A or B, because both will have the same value, because this is as long as A not equal to B. So I will return. What to return? What to return is A, or you can return B. Let's see whether this works. If in case I go and execute, or sorry, I have to call this, so I'll just call that Euclid GCD. Okay. If I execute, watch, then you can notice 20, 50. If I press enter, 5. Clearly it works. Let's give a larger value. 173, 133. If I press enter, then you can see 1, because that is only common divisor. So perfectly it works, but it is definitely more efficient. But what is the time complexity really of this? How are we going to analyze? Let me show you. Now let us analyze the time complexity of this. See, it's very simple. You don't have to count the frequency and all. If you look at this, let us assume I have two values, A and B. A is 13, B is 1. So according to Euclid's, what will you do? You are going to subtract 13 minus 1, you will get 12. You are going to replace A, which is 13, by 12. Next step, again the larger number is 12. So 12 minus 1 is 11. You will replace A by 11. Again the larger number is 11. 11 minus 1 is 10. Like that you will replace A with 10, and this will continue till A becomes 1, B becomes 1. Would you agree with me? Right? So basically if you look at it, you had A's value was 13. Now from 13 it had to go all the way till 1. Which means, wouldn't you agree that a minimum of 13 times it executed? Minimum of 13 times it executed. And why 13? Because 13 was the largest number. 13 was the larger number here. And please understand, this values that I've taken is the worst case, I hope you're able to think. Whenever you analyze the time complexity, you must think about the worst case. Worst case, if I have values like this, whichever number is the largest number, that many times it will execute. Which means, I can't tell n times, or I can't tell A times, I cannot tell B times, because A could be largest or B could be largest. So don't you think I can say that, hey, this will execute for big O of whichever is the maximum value of A comma B. So big O of max of A comma B times it will execute. If A is maximum, then A number of times. If B is maximum, B number of times. So big O of max of A comma B. But at the same time, I don't think that you have to think too much about this, because it is efficient, no doubt it is efficient. That was the worst case values. But if you take normal values, for example, let us take the brute force approach. A was 20, B was 15. how many times did it execute? So you started from min, you went all the way till 1. So it will not go till 1, 15, and the greatest common divisor here is 5. So you can see 10 times. 10 times it executed to find the GCD of your numbers 20 and 15. But if you take Euclid's, same A is 20, B is 15. But you can see it has only 3 steps. It has only 3 steps. Within 3 steps it was able to calculate. So 10, 3, 7 steps difference. So it's not like Euclid's is not efficient. It's just that when you calculate time complexity, you must always think of worst case situations. And what I showed you was something which was worst case. So this is big O of min of A comma B. This is big O of max of A comma B. I hope you're able to think. Any confusion till this? But luckily, there was another great mathematician who did not stop where Euclid stopped, looked at Euclid's algorithm and realized that it could be made even more efficient. What am I talking about? Let me show you. Now, Gabriel Lame was that mathematician which decided to make Euclid's algorithm even more efficient, because he noticed one thing, which is, let us assume I have a large value like this, right? Now, if in case I use Euclid's algorithm to calculate, the number of subtractions it will take will increase, and you know it is to the tune of big O of max of A comma B, right? Now, he wanted to make it even more optimized. So what he did is he studied Euclid's algorithm closely, and he realized that if he changes one operation, the time complexity is going to reduce significantly and it is going to become much more efficient. What do you mean, sir? Can you show it? You may ask. Let me show you. Now watch it, guys. It's very simple, right? I'm going to execute the code. Now this is the output that I have. Now what you must understand is I will give A as 20 and B as 15. Now in Euclid's algorithm you have to just make one change, which is you found the larger number, which in this case is 20, but now you must not subtract the larger from the smaller. Instead, you must divide the larger number by the smaller number and you must find its remainder. And if in case you look at it, 20 mod 15, if I do, I'll get the remainder. And what is the remainder? 5. I hope you're able to think. Replace the remainder with the larger number. So 20 is replaced by 5. I hope you're able to think. So now you have 5 and 15. Again, the larger number is 15, divided by the smaller number, which is 5, and find the remainder. The remainder is 0. Replace the larger number with this remainder. So 15 is the larger number, it becomes 0. The moment one of the number becomes 0, stop. The moment one of the number becomes 0, stop. And the non-zero number will be your GCD. Look at that. The non-zero number is a GCD because A has 5. And that is only our GCD. How are we able to think? The beauty of this approach is, even if the numbers become larger, not a problem. Let me assume A is 13, B is 1. Let me assume A is 13 and B is 1. So watch it. I'll just re-execute it and make it as A13 and B1. Re-execute it, make it as A13, B1. Now, if you notice, it's very simple. Here also, 13 and 1 I have. Now, look at the way. Larger number is 13. Mod smaller number 1. Remainder is actually 0, because you know it's perfectly divisible. The moment you get 0, take that 0, assign it to the larger number. So A becomes 0, B is 1, which is the non-zero number? B. B has 1 and 1 is your GCD. So fast it calculated. But if this was your regular Euclid's algorithm, then 13 times it would have done subtraction. So clearly, don't you think this is efficient? And hence, this is the algorithm all of you must close your eyes and use whenever in any situation you have to find the GCD or the HCF of two numbers, which is the optimized Euclid's algorithm given by the great mathematician Gabriel Lame. I hope you're able to think, right? Now, how to write code for this? Let me show you. Watch it, guys. Euclid's algorithm, it's Euclid's itself. It's just that instead of subtraction, whenever you find a number is larger, you divide it by the smaller number and take its remainder and replace the number with the remainder. So if I want remainder, I'll make it as mod. That's it. Mod and mod. significant difference will occur here. Any confusion till here? Now if in case I were to just, of course I've called Euclid's GCD, you can see, I've called it. If in case I just execute it, then clearly you can notice if I give 20 and 15, then clearly it is going to work. Oh, it is saying exception. Why is it giving an exception? Let us see, arithmetic exception. Now it gave an arithmetic exception. Scroll that side, scroll, show the exception properly. Division by 0. Why do you think this happened? Division by 0 happened. Correct, because sometimes, if let us assume A was 13, B was 1. Go back, click here. A was 13, B was 1. Right? Click there. If I do this, then 13 mod 1 is 0. You will put this here. How are you able to think? Now, the next time when you do, you are actually dividing a number by 0, because A is 0, B will be the larger number, which is 1. Then B, you are dividing it by 0. Take the cursor here. B, you are dividing it by 0. How are you able to think? If you do this, any number divided by 0 is infinity, and that should not be allowed. And because that is not allowed is why you got arithmetic exception, is why it's not as simple as just changing minus to mod. This has to keep happening not as long as A and is not equal to B. You must keep doing this as long as either A or B is not equal to 0. Because the moment one of the numbers becomes 0, you must come outside. You must come outside and return the non-zero number. I hope you're able to think. So what am I going to do is, I'll remove this condition and I'll make this as long as A not equal to 0 and B is not equal to 0. How are you able to think? If I add this condition, never for 0 values division will happen, which means arithmetic exception can be avoided at all costs. But at the same time, if in case I come outside, every time should I return A? Because previously in Euclid, both the numbers would become equal. So whether you return A or B, you will get the same GCD or HCF. But this time, one of the numbers will be 0. That is when you stop. The other number will have your GCD. So you must always return the non-zero number. And that is why before returning, you must put a if condition. I will tell if in case A is not equal to 0, then A is the GCD. I'll return that. I'll return that. Else, it means B is not equal to 0, so I'll return B. I'll be able to think. One of the numbers will be not equal to 0, and then there will be a GCD. I hope the changes which we have made is clear. Now, if in case I execute it, clearly you can notice if I put 20 and 15, within a second I'm going to get 5. Even for larger numbers, for example, if I re-execute, I put 1733 and 1333, and you know it should be 1, right? If in case I press enter, it will give me 1, and internally the computer is thanking you with folded hands for making its life easier, because the number of steps it has to perform has significantly reduced. However, what could be the time complexity of this code? Let's analyze. Now, the analysis of the time complexity of Euclid's algorithm, you have to use a little bit of your mind, okay? Because it's not as simple as how we were doing other things. And even otherwise, usually whenever you use Euclid's algorithm, you will be writing it recursively. You will not be writing it iteratively. When you use loops, it's called iteration. When you use recursion, it's called recursion. I hope you're able to think. So when we take up recursion and a deep dive into the concept, we will solve the same thing recursively as well. But for the time being, how to analyze the complexity? I'll just execute the program. I'll give two values for A and B. Now, I've made a small modification to the code where every time it will show you what is the value of A and what is the value of B. If I press enter, simple system.out.println statement, GCD between 12 and 8 is 4. But as you can see, A was 12, then A became 4, B was 8, and it became 0, which means if you look at it carefully, A value, let me just write A value, B value. A value was 12, from 12 it became 4, B value was 8, from 8 it became 0. So clearly you can see If I were to divide a by 2, if I were to divide it by 2, make it half. If I made it half, this would have been 6. But here I am not dividing it by half. What I am doing is I am doing a mod b. I am doing division with b. I hope you are able to think. So every time you can notice the value of a variable is reducing less than half. The value of a variable is reducing less than half. If I were to divide 8 by 2, I would have got 4, but you can see I am getting 0. Which means, don't you think it's reducing less than half? Half or less than half? Approximately you can say every time it is reducing by half. Which means one way I can say that whether I say a divided by 2 or whether I say b divided by 2, this is always greater than whether if I do a mod b or if in case I do b mod a. So what I am trying to say is this operation is always going to reduce the value of a and b less than half. Less than half it is going to reduce. And whenever values in an iteration is reducing less than half, you can close your eyes and approximately tell that it is a logarithmic time complexity. Because if you ask me, sir, how would the graph look like? The graph, my dear friend, would look something like this. So let us assume this is time and this is the value of n, right? This is n and this is my time. Logarithmic means this is how the graph would look like. It would look something like this. What you're noticing is that it's not linear. It's not square, it's not cube, it's not root n. And as you can see, as the value of n increases, for larger values of n, time is not significantly increasing. It remains almost the same. This is logarithmic. As values of n increases, time is not proportionally increasing. Are you able to think? Which means you can 100% say that the time complexity is big O of log of, and you can just say min of a comma b, like this you can say. A comma b. How are you able to think? Irrespective, just remember, if anybody asks you Euclid's algorithm, what is the time complexity? Tell it's logarithmic time complexity. And just keep a simple thing in mind that every time the values are reducing by half or less than half, which always makes it logarithmic. I hope you're able to think. Anyways, I hope this is also crystal clear to all of you. We have looked at the approach of Euclid's where we have used the brute force approach, then we use the Euclid's approach, then we use the optimized Euclid's approach. And I hope the time complexity of all three is also clear to each and every one of you. Anyways, this is just the beginning. We have many more really cool algorithms to learn. See you in the next class.